Greetings, fellow mathematicians. This is going to be brutal. This is the worst possible type of example you can get for a partial fraction decomposition question. It involves repeated quadratic factors. Many of my students have just run from the classroom when I put this example on the board. But we're going to go through it. We're going to take our time so that way you can be successful with it. So let's just get right into it. Fortunately, the math gods have smiled upon us and given us a factor denominator. So at least we have that going for us so far. We can jump straight to the partial fraction decomposition. All right, we have a mix of linear and quadratic factors. We have a linear factor, x. We'll get a partial fraction a over x. And then we have a repeated irreducible quadratic factor, x squared plus 4. Our first partial fraction would look like bx plus c over the factor x squared plus 4. And since that factor is repeated twice, we include another partial fraction with our denominator now squared. So we get two more constants, dx plus e. If in your course or on your exam, if you see like a third or fourth power there, you'll know you've really pissed your professor off. Fortunately for us, it's only a second power. All right, we're going to do the same first step. We're going to eliminate fractions. Just be careful. You have a slightly more complicated LCD with that power of 2, so just be careful with factors that you're canceling. Multiply your whole equation by the LCD. Should be left with the numerator 1. Here, your factor of x cancels, leaving you with a times x squared plus 4 squared. Go to your middle partial fraction. 1 factor of x squared plus 4 cancels, leaving you with bx plus c. And then times the remaining factor of x and the remaining factor of x squared plus 4. And we go to our last partial fraction, multiply that by the LCD. X squared plus 4 squared cancels completely, leaving you with just a factor of x multiplying that numerator. So we add to that dx plus e times x. All right, for this type of example, repeated quadratic factors, I advise against using the plugging in method. Because if you pick wrong values for x, although there are no wrong values, but if you pick them kind of not correctly or not doing it by thinking ahead, you could end up with some very large numbers there. 3 squared plus 4 squared, that can get out of hand very quickly. So we're going to use equating coefficients, and we really have no choice but to multiply all this stuff out. So let's go ahead and do that. I'm going to take my time like I would in class. I'm not going to try to do too much at once. So let's at least FOIL or expand this. We'll keep the a in front. So a, and then in parentheses times x to the 4th, plus 4x squared, plus 4x squared, 8x squared, and then plus 16. All right, we have a lot of options with this middle part. Let me just go ahead and multiply the x into the parentheses. So we're going to distribute. And that's it for the middle part. We'll have plus bx plus c. And now when we distribute that, we'll get x cubed plus 4x. And this last part, we can multiply that out, no problem. Distribute your x in. Looks like we should get dx squared plus ex. All right, we still have some more multiplying out to do. So you can multiply your a through the parentheses. Ax to the fourth plus 8a x squared plus 16a. This middle part, that we can FOIL. Looks like we get a bx to the fourth. Looks like we get, what is that, 4bx squared. All right, we now go to our inners, cx cubed. And go to your last terms. That should give me 4c times x. All right, and we have these terms, which we're just bringing down. We already multiplied them out. So plus dx squared plus ex. All right, hopefully not too bad, especially if you take your time. We have a lot of like terms here. We're going to collect them all together. And if we just quickly scan through there, we have x to the fourth, we have x cubed terms, x squared, x's, and then just constants. So let's go ahead and start with the x to the fourths. And I'm going to use that method where I'll cross off the terms that I've already used. So let's go ahead and collect our x to the fourth coefficients. We have an a. And where else is there an x to the fourth? We have b. And I think that is it. So that's it for your coefficients of x to the fourth. Now we can move on to our x cubed terms. So I'm just going to scan through there. We have an x cubed with coefficient c. All right, where's my next x cubed? That's it. So there was only a single x cubed. That's nice. I can actually write that without parentheses. So c x cubed. Next, we're going to look at x squareds. Looks like we have an 8a. Where's your other x squared? We have 4b. So cross that out. And do we have any other x squareds term? Yes, we have one right there with coefficient d. So plus d. And that's all times x squared. All right, it's getting a little bit easier to see terms now that most of them are being crossed off from what we've already used and included here. Next, we're going to look at our coefficients of x. So where's the first one? Right here, we have 4c. And we do have another x term, in other words, just x by itself to the first power, right here, ex. So we can put that coefficient e inside, and what should be left that's not crossed off are just the constants with no x's attached to them. And notice we just have a single one right in the middle there, 16a. And at the end of this, with the crossing out technique there, everything should be crossed out, indicating that you've included it somewhere in your work there. All right, now this is the work for implementing equating coefficients. The tricky part, students usually wonder, all right, I have powers of x on this side, but where's my powers of x on the left side? Well, you can always include missing powers of x with a coefficient of 0. So let's go ahead and rewrite this, including some 0 coefficients in front there, like 0x to the fourth, 0x cubed, 0x squared, and 0x, and we'll get our equations from there. If you're ready, let's go ahead and tackle this beast of a system of 5 equations involving 5 unknowns. Now again, The left side looks a little bit weird because there's only a 1 there, but let's rewrite it so that way we have powers of x. Any powers of x that are missing, you can include with a 0 coefficient. So let me rewrite this as 0x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1. And now we can start to equate coefficients of x on each side. We're going to start with x to the 4th powers and go down from there. All right, I like to write down my equations from where they come from. So we get one equation from the x to the 4ths, one from x cubed, another from x squared, another from just x, and then our last equation comes from the constants. Now, the fact that a lot of the powers of x were missing there means almost all of our left sides of these equations will be 0, which is at least one benefit of having to deal with a system of 5 equations and 5 unknowns. So your x to the 4th coefficients, left side, that coefficient is 0. And on the right side, your x to the 4th coefficient is a plus b. All right, we can go to now our x cubed terms. So we have a coefficient of 0, and that should equal this coefficient of x cubed, c. And notice that is really nice. That tells us one value for free. That tells me immediately that c equals 0. Now, I chose this example to kind of take pity on my calculus students. Hopefully, your professor takes pity on you too and gives you a few coefficients that are 0. All right, so let's keep going. We go to our x squared coefficients, 0 for your coefficient on the left, and on the right side, 8a plus 4b plus d. All right, let's keep going. We go to now our x coefficients. That's still 0 on the left. And on the right side, your x coefficient is 4c plus e. Let's pause for 1 second. We already know the value of c is 0. Plug that in here. That immediately implies that e is 0. So that's really nice, because already we've gone from 5 unknowns down to now only 3 unknowns left. We just have to find the values of a, b, and d. All right, and our last equation, the constants, now there is a coefficient there, a constant of 1. And that should equal your constant term on the right side, which is just 16a. And again, notice this one immediately tells you that a is 1 over 16. All right, so what do we have left to determine? We don't know b and we don't know d. Well, let's think of what we know. Let's scan through our equations. This one is really nice. With the value of a as 1 over 16, that immediately implies, due to the 0, that b should be negative 1 over 16. And at this point, we only have one unknown left, finding the value for d, where we're just going to plug in the values that we currently know, which are a and b. And we'll get a very simple equation for d. The equation that we get is 0 equals 8 times a, where a is 1/16. And then we have plus 4b, so plus 4, and then times negative 1/16, and then plus d. All right, looks like we can reduce these fractions pretty quickly. Looks like this one will reduce down to just 1 over 2. And here it looks like we get minus 1 over 4 plus d. And this shouldn't be too bad, even though there's fractions. Looks like this comes out to be what? Geez, basic math here. A half minus a quarter, 1/4, positive 1/4. And that's plus d. And whew, all right, that's done. We get d as negative 1/4. All right, and that is solving our system of 5 equations for 5 unknowns. I would put this in the medium to high difficulty range for what you could expect for an exam question. That's about as complicated as I would make it for one of my Calculus 2 partial fraction decomposition exam questions. Now that we have our values for a, b, c, d, and e, let's plug them in and get to these integrals. Now notice the fact that we have c and e as 0, that eliminates how many terms we have to integrate. And that's pretty nice. So let's write down the integrals that we have to calculate, the terms that do remain. So we have a as 1/16. So we get 1 over 16 times 1 over x. The b term is negative 1/16, but c is 0. So I can write the next one as minus 1 over 16 x over x squared plus 4. And similarly, d is negative 1/4, but e is 0. I can write this last one as minus 1/4 x over x squared plus 4 squared. All right, and again, your work here comes down now to evaluating 2 integrals. The first one, very straightforward. Again, a natural log of x. Linear factors always will integrate to natural logs. And let's go through the work for these 2 integrals. Now, we have 2 integrals to evaluate, but if you're on top of your basic integration methods, we can use the same u substitution. So let me stack the 2 integrals, and we'll use the same u substitution twice. All right, so for our first integral, we'll ignore the fractions in front and just focus on x over x squared plus 4, and then x over x squared plus 4 squared. All right, our first integral, x over x squared plus 4. And our second integral, x over x squared plus 4 squared. All these repeated quadratic factors, I kind of get out of breath when I'm teaching. It's a lot to say. All right, our substitution here will be u equals x squared plus 4. And that will work for both integrals. And that is because both of them have that factor of x, which we're going to want for du. Du here comes out to 2x dx. There's no factors of 2 there. Same trick that we've been doing in a lot of other examples. Divide the 2 over 1/2 du equals x dx. All right, let's tackle the first one with our substitution. We can rewrite this as 1/2, 1 over u. And we've seen that a lot. That integrates to natural log of u. And back substitute u as x squared plus 4. All right, so that takes care of the middle integral. Don't forget to multiply by the negative 1/16. And then the last one, we can also use this same u substitution, but it's just going to convert to a different antiderivative that we need to calculate. It's not going to be 1 over u, but you can probably see you're going to get 1 over u squared. So we used our work here to convert to there. And let's go ahead and use this substitution, our work, to convert this x integral into a simpler u integral. It's virtually identical. X dx, we're going to replace with 1/2 du, but we get u squared in that denominator. So 1/2, 1 over u squared du. Let me go ahead and rewrite the 1 over u squared as u to the negative second power. And if we go ahead and integrate that with the power rule, looks like the 1/2 stays as a constant multiple. Add 1 to the power, we get u to the negative 1. And then we divide by the new power. We're dividing by negative 1. And just to make my answer look as clean as possible, I like to rewrite the negative exponents as fractions. We can rewrite that as negative 1/2, 1 over u plus c. And then back substitute your same u that we used. U is x squared plus 4. All right, and that is pretty much all of your work here. Let's just highlight the antiderivatives that we just calculated. We need this part, and we need that part. We just need to plug those back in here, and we are basically done. Again, don't forget to integrate the first term. I sometimes have even my best students focus on the tricky integrals, and they forget to integrate the first one. So that's going to integrate to 1 over 16 times natural log of x. Let me not try to do too much work. Let me just put the negative 1 over 16 there. And then the antiderivative for x over x squared plus 4, that as a half. So we'll clean that up a little bit later. So times 1/2 natural log of x squared plus 4. We have the minus 1/4. And what is our antiderivative? Negative 1/2. So I guess we can go ahead and change that to a plus. And that's 1 over x squared plus 4. All right, and if you clean up your fractions here, looks like we can go ahead and replace this part here with 1 over 32. So minus 1 over 32, natural log of x squared plus 4. And geez, basic math. I get so focused on all the calculus and integrating, sometimes I forget the basic stuff. Looks like we get 1/8 1 over x squared plus 4 plus c. And that is a really good example. It is complicated. There's a lot of steps. There was a fair amount of algebra, 5 unknowns, which requires 5 equations, and then some moderate work for the integrals. But if you have mastered everything for this problem and you feel good about it, you should be completely fine for any and all problems that you could be given for partial fraction decomposition. Hope you enjoyed the video. Support the channel, like and subscribe.